The book The Drunkard's Walk presents a puzzle about the probability that a father who has two children, one of whom is a girl named Julie, in fact has two girls. The YouTube video by Zach Starr entitled "This May Be the Most Counterintuitive Probability" picks this up directly from the book and presents very interesting exposition of the topic. I had read the book, but was reminded again by the video. If you find you're really interested in this problem, please be sure to watch the Zach Starr video for the backstory. My purpose here is to compute the probabilities for a more general case based on reasonable assumptions and to draw a few conclusions that I hope will clarify the original paradox. Let's begin with a less paradoxical problem to set the stage and have something to compare it to. Suppose you meet a man who says, "I have two children, at least one of whom is a girl." What is the probability that the man has two girls? The answer is 33 1/3% because there's only one way of having two girls, and the total possible ways of having two children, at least one of whom is a girl, where order is important, is boy, girl, girl, boy, and girl, girl, are three equally likely ways. That is, the probability equals 1 out of 3 equals 33 1/3%. Hence, knowing that the man has at least one girl increases the probability to 33 1/3% from 25% when there's no additional information. Now, consider the following event. You meet a man who says, "I have two children, at least one of whom is a girl whose name is Julie." What is the probability that this man has two girls? Now, a number of you will be convinced that we have already given up the game, convinced that the father must have two daughters. If that is what you think our statement of the problem has done, consider the following refinement. Suppose that you are at a party and speak to a man who mentions that he has two children. Before you can say anything, the host of the party rushes him away to meet someone arriving at the door. The man talks to the new arrival for a moment, and you overhear him say, "You have two children too?" Girls in this case, we are told, is now 50%, and this is the paradox. How can adding the name of a daughter increase the probability of the father having two daughters from 33 1/3% to 50%? How can adding the name to the information that the father has at least one girl increase the probability 16.7 percentage points? Perhaps putting it this way makes it sound less surprising. Maybe if we actually demonstrate more clearly how the name information is informing the calculations, the mystery will disappear entirely. To start down this road, let's compute the probability according to the approach just employed in our initial example, which is how it was computed in the book version, by the way, to see what we can discover. Let G sub j represent the girl named Julie, and G sub a represent a girl with any other name. Then the number of ways to have two girls, one of whom is named Julie, is G sub j, G sub a, and of course G sub a, G sub j, or two equally likely ways. The total number of ways is B G sub j, G sub j b, G sub j, G sub a, and G sub a, G sub j, or four equally likely ways. So the probability of two girls is 2 divided by 4, or 1/2, and we'll call this the original solution. Notice that in the original solution we have a number of selections of girls and boys that seem to be with replacement. Of course, this is an important hidden assumption, and one of the first assumptions that is, strictly speaking, incorrect. And the second important and strictly incorrect assumption is that these probabilities are equally likely. Maybe these false assumptions explain something, or maybe not. We'll see. To make our contribution to this problem, we will also make several assumptions, which I will now enumerate. The sample space is the set of all two-sibling pairs of people, where each pair consists of a girl named Julie and either a boy or another girl not named Julie. The girls are selected as individuals, but the same name cannot appear twice in the two-sibling pair. The boys are selected at random, but again, the boys cannot be selected twice. The same boy cannot be selected twice. The girls' names are assigned uniformly and at random. Let's assume that there are M girls' names, G1 through GM, and cap N total girls. One of these G's represents a girl named Julie, and we will call it G sub J. There are approximately as many boys and girls in our everyday population, the one we would like to model, so the total population in our model would be 2 cap N children. Now we can create a tree of probabilities, but we don't need the entire tree, just the portions that have G sub J in them. The probabilities are the probability of B first and G sub J second is cap N over 2 cap N, because there are half of the children are boys, and there are in other words, there are N boys. And cap N times cap N over little m, which is the number of girls that have the name Julie, divided by 2 cap N minus 1, because we've already selected the boy. And that total equals cap N divided by the quantity 2m times 2 cap N minus 1. All right, selecting the other way, Julie first and then the boy, G sub J, B, you end up with the probability 1 over the quantity 2 times the quantity 2m minus 1. Notice it's not the same as the one we just did. That's because we're doing it without replacement. On the other hand, if you look at the probability of G sub A, G sub J, you will see that the probability is the quantity m minus 1 divided by the quantity 2m times the quantity 2m minus 1. And you will see that if you do it the other way, probability of G sub J, G sub A, you'll get the same probability. And as I said, the value cap N over m gives us the number of girls having each name. We subtract that value at points because no name can appear twice in the pair. This is consequence of not permitting duplicate girls' names. So the probability is the sum of these, which is 8m cap N minus 5 cap N minus 3m plus 2 divided by the quantity 2m times the quantity 2m minus 1 times the quantity 2 cap N minus 1. That's equation 6. To get the probability of 2 girls, given that we have G sub J, we must normalize the unconditioned probability of having 2 girls, of which one was G sub J, by these probabilities. That unconditioned probability is just the last 2 expressions added together. So we have the expression, the quantity m minus 1 over the quantity m times the quantity 2m minus 1 multiplied by the inverse of the total probability from the last page, and that equals 2 times the quantity 2 cap n minus 1 times the quantity m minus 1, all divided by the quantity 8m cap n minus 5 cap n minus 3m plus 2. Here we let cap n approach infinity and get 4 times the quantity m minus 1 divided by the quantity 8m minus 5 for the probability of getting 2 girls, given that one of the girls is named Julie. Again, if we let m approach infinity, the probability approaches 1/2. We are able to take the limit sequentially in the general case since the limit does exist. We have a restriction to place on m that will make the existence of the limit in that case very clear. I will go into that in a moment. Note, the reason we normalize is that the sum of our probabilities for the branches containing g sub j above does not equal 100%. We must bring the probability for the case that one of the siblings is a girl named Julie up to 100% so that it represents the entire event. To do so, we must multiply by its inverse, and if we do that to the total probability for the event, then we must do so also for the component probability that there are 2 girls of which one is g sub j. The expression we derive from our assumptions, 2 times the quantity 2 cap n minus 1 times the quantity m minus 1, divided by the quantity 8m cap n minus 5 cap n minus 3m plus 2, which is expression 7, will provide us with 3 expressions for an accurate estimate of the probability of selecting 2 girls given that one is named Julie. The expression as it stands gives us a solution when we know both n, cap n, and m. The limit as cap n goes to infinity of the expression gives a solution when we know m and can assume that cap n is large. The limit of the expression as m goes to infinity gives us a solution when we can assume that m is large and we know cap n. So we've got all bases covered. Now we are ready to tackle the paradox and the original solution. First thing, let's try an intuitive solution that occurs to us that I think is interesting and instructive. We are grouping girls by name into M names and selecting exactly one girl from any of the names, that is, without replacement. For the boys, we are essentially numbering them from 1 to cap n and selecting them without replacement. So we can see that the boys individually constitute groups, each made up of one boy. We may believe that as the number of names for the girls increases, the ratio of the groups formed by the girls' names and the cap n pseudo-groups of the boys become closer and closer to 1. Therefore, when we select from these 2 sets of groups, it becomes more and more like selecting from individuals instead of groups. Then the probability of selecting a girl who is not named Julie is 50%, because girls are 50% of the total population, and the probability of selecting a girl named Julie is 0 because the population is infinite. And that's because the probability of selecting any particular discrete item in an infinite population is 0. Hence, if we know that a girl named Julie was selected in some order, the probability of selecting a girl not named Julie is 50%. Another way to say that is the probability of having selected 2 girls, given that we have one named Julie, is 50%, our probability, right? Unfortunately wrong. To see how wrong it is, notice that we could very well have restricted m by setting it to cap n divided by 2. And each name would belong to exactly 2 girls if we did that, no matter how large cap N became. In other words, the groups would not begin to look like a simple boy-girl population as N became large. This idea of setting M to a fraction of cap N will work in general. Let's let 0 be less than k less than or equal to 1, and M equals k times cap N. In this case, it turns out that when we replace M with k times cap N, we will still get 1/2 as the limit as cap N goes toward infinity for our probability. That is, the limit of the probability is still 1/2, even though the population doesn't look like a simple boy-girl population. Now in our particular problem, if we restrict ourselves to a large population, it becomes more likely that we could entertain the idea of making M a constant. For instance, letting M be equal to 45 as cap N approaches infinity might be useful, because that may seem like a good estimate of the total number of girls' names. For example, in the American population that would, as a group, fit the assumption of having equally likely probabilities. My top-of-the-head estimate of the number of names that are popular enough to be equally likely for a relatively large segment of the population, say 90%, is actually somewhere between 30 and 45. Then we could assign our M equal 45 to formula 7, giving 176 times cap N minus 88 divided by the quantity 355 times cap N minus 133. Then for the 90% we could apply that expression, and for the 10% we could apply the limit as N goes to infinity of our main result, 8, and we would get a 0.90 times 176 cap N minus 88 divided by the quantity 355 cap N. Minus 133 plus 0.10 times 1/2. We can plug in good estimates of cap N here. I have a top-of-the-head estimate of 10 million for the number of girls in the estimate. Plugging in that value of cap N gives a probability of 49.58%. Now, how important is the selection of M to the probability? Well, if we let M approach infinity, the percentage point difference in formula 8 between M equals 45 and M equals 300 is only 0.36, about 1/3 of a percentage point, so probably not very important for reasonable sizes of M. This suggests that we could eliminate M from the formula, which we'll do now. If we consider our formula without M, we can take the limit of the probability in 7 as M goes to infinity to find the answer. And it is the quantity 4 cap N minus 2 divided by the quantity 8 cap N minus 3. For what sizes of cap N will this be okay? It looks like we could be okay for most purposes so long as cap N is greater than about 19, even though we assumed N was large when we set M to 45 at the beginning of this section. Basically, again, for most purposes, a good estimate for the probability is simply 50%. At this point, I want to tackle the question about the importance of assuming equal probabilities. You will remember that the way the original probability was computed, that is, selecting GA, G sub J, G sub J, G sub A, from B, G sub J, G sub JB, and so on, where all the choices are assumed to be equally likely. But as a matter of fact, since selecting B is much more likely than selecting G sub J, and somewhat more likely than selecting G sub A, we might think it likely that there might be a significant difference between selecting G sub JB and selecting G sub J, G sub A, for instance. However, consider the following. Compare the following model to the original solution by assuming there are 45 names as before, one for each of 45 girls, and assuming sampling with replacement just as in the original solution. Then we have probability of G sub A, G sub J equals 44 over 90 times 1 over 90, which is 0.54%. And we have probability of G sub A, G sub J equals the probability of G sub J, G sub A. So we can reverse the selection and they're equal. We have probability of G sub A, G sub A, where we pick A twice, and we get a probability of 23.90%. The probability of B, G sub J is 0.56%. And we can also select either direction, B, G sub J, or G sub JB, and they're equal. Using Bayes' rule, which we've been doing all along without saying so, we have two girls given G sub J equals 49.13%. Notice that we have used the fact that that the probability of G sub A is 23.90%. We actually used that when we compute it using Bayes' rule. So it's involved in the probability. Notice that we have ignored the population size in this model. That is because we are sampling with replacement, so the population is essentially infinite. Also notice that the probability are not strictly equally likely. However, we see that probability of G sub A, G sub J is equal to the probability of G sub J, G sub A, as I said, which is approximately equal to the probability B, G sub J, which is equal to the probability of G sub J, B, as I said. And probability G sub A, G sub A is approximately equal to 0.25, which means it's about 1/2 times 1/2, which is the probability of selecting a boy. So the large probabilities compensate for the small probabilities. We might ask, does this happen in general? And the answer is yes for this problem, as long as m is greater than 2. Compare the following. Probability of B, G sub J is equal to m divided by 2m. You can see that for selecting the boys, times 1 divided by 2m. And the probability of selecting G sub A, G sub J is m minus 1 over 2m over 1 over 2m. And you can see that the probability of G sub A, G sub J is approximately equal to the probability of B, G sub J if m is greater than 2. Now, for those unfamiliar with the Bayes formula, Bayes' rule, I want to quickly present the general formula for the simple Bayes' rule, namely, the probability of event A given that event B has occurred equals the probability of event B given that event A has occurred times the probability of event A divided by the probability of event B. I must admit I cheated a little bit. I expressly disallowed G sub J, G sub J. while allowing the possibility of G sub A, G sub A, where the A may represent the very same name. Say both girls are named Carla, for instance. Let's use binomial probability to treat these calculations, which we allowed these possibilities back in. I want to do this because it is a very simple way to play with the assumptions. What we can do is take the quantity B plus G sub A plus G sub J and square it and get the values B squared plus G sub A squared plus G sub J squared plus 2BG sub A plus 2BG sub J plus 2GA GJ, where B, G sub A, G sub J are the probabilities of choosing a boy, a girl not named Julie, or a girl named Julie. Then B squared means choosing two boys. G sub A, G sub J means choosing a girl not named Julie and a girl named Julie in any order. If we include the possibility of two Julies and two any other names, the probability becomes the probability of two girls given G sub J there equals G sub J squared plus 2G sub A, G sub J divided by the quantity G sub J squared plus 2B G sub J plus 2G sub A G sub J, which is equal to 2M minus 1 divided by the quantity 4M minus 1. However, when M equals 2, the probability of two girls given G sub J is equal to 3 over 7, which is 42.86%. If we exclude G sub A squared and G sub J squared, then the probability is G sub A, G sub J divided by the quantity G sub J plus G sub A, G sub J. The 2's cancel out, which is equal to the quantity M minus 1 divided by the quantity 3M minus 1. And for M equals 45, this is 32.84%, which is trying to be 33 1/3. And for M equals 2, it is exactly 20%. Therefore, including two Julies and two any other name seems to get to the original solution faster than any other assumptions. In other words, we have sampling with replacement, where all the sampling is independent and we allow in everything, so we can get the results almost by assuming some things that seem to be a bridge too far. Now consider the assumption that the probability of G sub A, G sub J equals the probability of B, G sub J when M equals 2 pictorially by drawing a tree and considering how we might justify saying that the branches are equally likely. Note that we might assume that M equals 2 if we are considering only the names Julie and any other name. In fact, I think we're led to assume that, and that's part of the problem. We have to decide on our assumptions, and from what we've learned, the best we can do for the probability when M equals 2 is 42.86% when we allow in everything and sample with replacement. So let's look at the tree in that case. All right, for the tree, we have on the left top, we have B, G sub J. All right, there are 50% chance of selecting boys, so 1/2. And there's a quarter chance of selecting G sub J, so that's 1/4. Multiply those together, you get 1/8. I put that in a circle. And for G sub A, G sub J, it's 1/4 times 1/4 or 1/16, and so on. Notice that I have G sub J, G sub J in there, and it's 1/16. All right, I've circled all the when I multiplied out the probabilities, I've circled them all. Notice that if you add the probabilities in a circle, you'll get 7/16. Well, I want this to represent the entire event of selecting two children, with one being Julie. So I have to norm this by 16/7 in order to make it 1. If I do that, I multiply each one of those probabilities by 16/7, and I'll get 2 7s for the first one, 1 7 for the second, 1 7 for the third, 2 7s for the fourth, and 1 7 for the fifth. If you add those up, you'll see they add up to 1. All right, the probability of two girls given that I have a girl named Julie is now equal to 3/7, or 42.86%. And again, I have Julie twice. So that's not very satisfying, but that's what we had to do. Now, but notice that the probability of a boy and a girl named Julie, B, G sub J, is twice the probability of a girl with any other name and a girl named Julie. So they're not close to being equally likely. Now, so we've given every benefit of the doubt to the original solution, but have not found any way to justify it, short of assuming that we know we're dealing with a large population and that the probability of G sub A, G sub J equals the probability of B, G sub J for large populations, where the meaning of population isn't clear because the paradox doesn't specify anything about the girls' names. The solution doesn't specify anything about the girls' names. I'm not willing to assume all that. Hence, I'm willing to conclude that the original solution is bogus. According to what we've shown here, the claim that the probability is 50% made by the original solution is essentially true for 20 less than m, less than or equal to cap n. I'm not disputing that. I'm just saying that the assumptions implied by the calculation are wrong or misleading. In other words, the calculation does not prove its case. The paradox, however, does exist when 20 is less than m is less than or equal to cap n, approximately. And I think we can see why. The probability of G sub A, G sub J approaches the probability of B, G sub J, as we have seen when m gets large, so that the equal probability approach of the original solution begins to make sense. So in that sense, the original solution is correct, but the assumptions that would allow the solution to take credit are nowhere to be found. At this point, I think I've done everything I set out to do. I've determined that a reasonable model of the population of the probability of having two girls, given that we have a girl named Julie, rapidly approaches 50% as the size of the population approaches infinity. We realize that when m is large, the probability becomes approximately equal. This is an intuition. We were also able to recognize and reject an incorrect intuition. We have determined that the original solution does rely on equal probability, assumes something like sampling with replacement, yet gives the same answer as our limit results, which are based on probabilities and sampling without replacement. Notice I don't say assumes because we took the limit. I don't think it assumes that when you take the limit. At the same time, we determined that we don't have to explicitly include the number of possible names in our solutions when we look at real populations, but if we don't, we still must consider them by taking the limit over the possible names or otherwise making assumptions that account for the names. Alternatively, we found that we can base our derivations directly on the possible names and sort of ignore the size of the population, etc., and along with sampling with replacement, achieve a result very similar to the limit at the limit to the original solution. However, our most important finding was that the original solution's implicit assumption of equal probabilities, that is, probability of G sub A, G sub J equals probability of B, G sub J, when M equals 2, makes it misleading and or actually wrong. And this constitutes all my ideas and all my explanations concerning this paradox. I hope it is helpful to you. There are other explanations and ideas concerning the paradox out there, so if I haven't dampened your interest with all the calculations, please take a look at some of these other approaches and let me know what you think. I would love to hear from you about this problem if you have time to leave a comment.